Hi, my name is Talia, and I am an incoming high school senior, and I'm very passionate about chemistry and math and helping people learn both chemistry and math. I want to pursue a career in chemistry and math education, and I started this YouTube channel as a supplemental learning device to anyone who might be having difficulty learning chemistry. I've been going in order of the topics that I learned in honors chemistry and basically teaching them again to you guys. In this video, we will be learning about temperature and significant figures. In my previous video, I discussed scientific measurement and conversions, and I hope you enjoy and are able to learn a little bit more about chemistry. Let's get started. So the first part of our topic today is temperature. We have Fahrenheit, Celsius, and Kelvin. So as you can see on this chart, each unit of temperature has a different boiling point, a different freezing point, different room temperature, stuff like that. And we are going to learn how to convert between the different units using these equations. So most often in chemistry, you will see Kelvin because there is no negative temperature. So you will not get negative answers when you use Kelvin. We can also convert between these units as you see here. We are going to be converting between all three units, so get your calculators out. So we are going to try our first example. We have 60 degrees Fahrenheit, and we are trying to convert to both Celsius and Kelvin. So if you look, the equation from Fahrenheit to Celsius is Celsius equals 5/9 Fahrenheit minus 32. So I'm going to write that equation down. So I wrote my equation down, and now I'm just going to plug in Fahrenheit. So I have 5/9 of 60 minus 32, and that equals 5/9 28, which equals 15 degrees Celsius. And we would not write 15.6, which is something we're going to discuss later. Now we're going to convert from Celsius to Kelvin. So to do that, we're going to add 273. Kelvin equals Celsius plus 273. And then we have 15 plus 273. And I would recommend that you keep the unrounded version in your calculator. So we will get 289 Kelvin. And that is our first problem. Next, we are going to go from Kelvin to Celsius to Fahrenheit. You have to first convert to Celsius from Kelvin because there is no equation going from Kelvin to Fahrenheit. So we can use the same equation we just used. And this can be rewritten as K minus 273 equals C. So I'm just going to plug that in. That equals 197 degrees Celsius. And then we can convert from Celsius to Fahrenheit. So Fahrenheit equals 9/5 Celsius plus 32. Now you have to make sure that with these equations, you take notice of the fact that from Fahrenheit to Celsius, Celsius is in its own parentheses, and you add 32 afterwards. Versus going from Celsius to Fahrenheit, you would first subtract 32 from Fahrenheit and then multiply by 5/9. So we are going to do Fahrenheit equals 9/5 Celsius plus 32. So we are going to just plug in Celsius once again, or 387 Fahrenheit. Usually you will just write the degree sign with Celsius. With Fahrenheit, you would just write an F. That is your answer for this problem. Finally, we are going to go from Celsius to Fahrenheit to Kelvin. So let's first go from Celsius to Fahrenheit. Let's switch it up. So Fahrenheit equals 9/5 Celsius plus 32, which is what we just did up here. So you can just plug in 56 to get 133 degrees, so 133 Fahrenheit. And like I mentioned earlier, keep in mind that you are just keeping order of operations in mind. So if I were to go from Fahrenheit to Celsius, I would, like this equation up here, first subtract 32 and then multiply by 5/9 because of these parentheses. So now we're going to go from Celsius to Kelvin. So K equals C plus 273. You guys know the drill. So if we add 273 to 56, we get 329K. And that is our temperature conversion practice. So now let's move on to reading metric scales. So with reading metric scales, you just want to make sure that you read one place past the smallest division, like this example here. Each line is 1, this is 26, this is 27, this is 28, 29, 30. You want to report to the nearest tenths place because that is one division past. Reporting to that decimal place, one past the smallest division, gives a new level of accuracy to the measurement. So you want to make sure that you always record your measurement one past the decimal, one past the smallest division. So with this example, as you can see, we have ones again. So this is 11 over here, 12, 13, 14, 15, as you can see. And you see obviously that this is a little bit above 10. So you could say 10.3, which is what this example did. If it was down here very descriptively on the 10 line, you would still need to write 10.0 milliliters because you need to report to the 10th place due to every line being by ones. So you need to report to one place past that division. So now we are going to move, here's another example. This ruler is in, every line represents a tenth. And you can tell that by seeing that there are 10 lines. So this is 10 lines. So, and the big numbers are 1 of difference. So if you were to divide 1 into 10 parts, each line is a tenth. This would be 10.1, 10.2, 10.3, 10.4. When you report, you want to report to the hundredths place because you want to report 1 past the smallest division. So that's just the big idea with these, 1 past the smallest division. We can give it a shot with this ruler. So you can pause the video here and try it on your own. So if we look, there's a division of 1 here. We see that over here we have 1.0, 1.1, 2, 3, 4, 5, 6, 7, 8, 9, and then this is 2.0. So if we have 10 divisions between one unit, each one of these represents 1/10. So if we go now to here, we can see that the ruler is about here, but it is not exactly at the 4.4 line. So I would say you should write an answer anywhere from like 4.37 to 4.39. Again, you don't want to write it. Let's say it was directly on the line. You do not want to write 4.4. That is incorrect. Because each line is a tenth, 1/10, you want to report to the nearest, to 100th. So on to our next example. Each one of these divisions is 1 unit. There is nothing in between, which means that we want to report to the tenths. I'm going to say that this is about 4.3. You could also say 4.4. Also, make sure that you are always putting your units. I forgot to do that with this last one. It's a pretty straightforward concept. You just want to be extra precise and report to 1 past the smallest division. So now we're going to move on to an overarching concept of chemistry, significant figures. So rules such as the ones we went over just now, those all come together in a concept of significant figures. And these significant figures are necessary because in chemistry, they represent how precise your measurement is. So 3.0 and 3.1, they mean different things in chemistry. And it's important that you pay attention to those rules when you're doing your calculations to make sure that your answer is conveyed as accurately as possible. So as I wrote here, significant figures should be applied to all calculations. So we are going to now discuss the rules for significant figures. I'll just list them. The first one is that non-zero digits are significant. The second one, zeros between non-zero digits are significant. So as you can see, 5,708 has a zero in between, but that zero still counts as a significant figure. So zeros before a decimal place are significant. As you can see, there's no decimal place here, and they're these two rules differ because 800 does not have any non-zero numbers after it, versus the zero in 5,708 has a non-zero number after it. However, in both of these conditions, the zeros are still significant. Also, zeros after a decimal place are significant. And this is where the thing I said earlier about how 21.0 and 21.00 mean two different things. So, because the amount of zeros after a decimal place adds to the significant figures, you want to make sure that you're not adding extra zeros. So, furthermore, leading zeros before or after a decimal place are not significant. Basically, these zeros do not count, this zero does not count. So that is why these two numbers have the same amount of significant figures, because all of these are insignificant and there are only two significant figures. Lastly, powers of 10 in scientific notation are not significant. So this is not significant. You just say this has 3 sig figs. Basically, these are the main ideas with significant figures. You're going to want to remember these rules, and they're pretty straightforward once you get to working with significant figures. So now we're going to do a practice with determining the number of sig figs. So you can try this on your own and just pause the video and join back with me when you're ready. Okay, so for our first example, basically this would use the rule that zeros in between non-zero numbers are significant. So we can count all of these digits as significant. We have 1, 2, 3, 4, 5, 6. So this number would have 6 significant figures. Next, we have a similar thing. This is not a zero in between non-zero numbers, but if you remember, zeros before a decimal place are significant. Therefore, this zero counts. So we have 1, 2, 3, 4, 4 sig figs. This is a zero before a decimal place, but it is a leading zero. It's not coming after a non-zero number. So none of these zeros count, and we only have 2 sig figs. Also, these zeros are also leading zeros because they don't come after a non-zero number. Our last example, same as the first example. Same as the second example. There are 3 sig figs because this zero is before a decimal place and it comes after a non-zero number. Okay, so we are now going to do a short introduction on rounding. And I know previously you have learned like 5 and above, give it a shove, 4 and below, keep it down low. And I'm just going to go over what you would do when you are given a multi-digit number and you're told to round to a specific place. So as you can see, the main idea is that the only digit that should be considered, the only digit that should be considered when you're rounding is the one directly following the digit being considered. So in this example, you are rounding to the nearest thousand. So we are going to look to the digit next to it, which is the hundreds. And that number should be considered when rounding. And since it is below 5, we are going to keep it down low. And then the whole rest of this number becomes zeros. And you're going to just write it as 1,000 because that is to the nearest thousand. So with this next example, we are rounding to the nearest 10. So we are going to consider the ones, which is the 8. And the 8 is above 5. So we are going to give it a shove, which would bring us to the next tens. But because this is 90s, that would also impact the hundreds. So we would just write this as 13,900. And then because it's 898, and then 98 rounds up to 100, which will push the next 100. Okay, so the same applies for sig figs. When you are given a certain number of sig figs to round to, you pay attention to the digit right afterwards. So we are rounding to 2 sig figs. I'm going to highlight the amount of numbers we want to round to in pink. And then we want to look at the digit after it, which is a 9. And because that is 5 and above, we would round to 4.6. So it eliminates these 2 sig figs and just pushes this 5 up to a 6. Next, we have 0.000868. Keep in mind that these 3 zeros are insignificant because they are leading zeros. Also, this 0 is insignificant for the same reason. So in order to round to the nearest 1, this is how many sig figs we want to round to. This is what we would consider. So this 6 would push the 8 up, and we would get 0.0009, and that is 1 sig fig. Next, we have 0.9950, and we are rounding to 3 sig figs. We have 1, 2, 3, and 4. And that 0 we would use to keep the 5 down below and rewrite this as 0.995. 6.89 times 10 to the negative 6. We have 2 here that we want to round to. And then we would look at the 9, which would push the 8 up to get 6.9 times 10 to the negative 6. Remember, you can also write this in decimal form because, like I mentioned earlier, leading zeros do not count as significant figures. Give the next 2 examples a shot on your own, and we will come back together to discuss them. So with 35,998, this first, to be in 2 sig figs, we would need to write in scientific notation, but we need to figure out what to write in scientific notation. So we want to have 2 sig figs, and we would look at the 9. The 9 is going to push the 5 up to a 6, and then we would have 3.6 times 10 to the something. But in order to do that, as you remember from our first video, we're going to go to the left and count how many times the decimal place is moved in order to get a number between 1 and 10. So we have 1, 2, 3, 4. So we move the decimal place 4 times to the left, which means to get in standard form, we would move 4 times to the right. So 3.6 times 10 to the 4th. Final example, we have 0.00003591. We are rounding to 2 sig figs here. We would use the 9 to round, which would push the 5 up to 0.000036. Okay, now we are going to move on to operations with significant figures. And this is the heart of how you will know whether to write 3.1, 3.10, 3.100, because how the given numbers that you have in the beginning of the problem will impact how many significant figures your final answer has. So we are going to start with addition and subtraction, and with addition and subtraction, you round to the fewest number of decimal places. So if you look in this example, we have 25.22 and 13.998, and as you can see, 25.22 has 2 decimal places, like numbers after the decimal place, and 13.998 has 3. This is the unrounded answer, but in order to express it properly in terms of significant figures, we are going to round to 2 decimal places. So you would consider the digit next to the decimal place you are rounding to, which would push the 1 up and make it a 2. So this is our final answer. So you can try this one with me. We would first plug in 75.6 minus 25.344. And as you can see, 75.6 has 1 decimal place. So you want to ask yourself the question, which number has fewer digits after the decimal place? The answer is 75.6 because there's only 1. So our final answer will only have 1 digit after the decimal place. So if you plug it into your calculator, you would get 50.026. That is the unrounded answer, but we are rounding to 1 decimal place. So we would consider the number next to the 0, which is a 2. That would keep the 0 down below, and we would write 50.0. Now we are going to move on to multiplication and division. So with multiplication and division problems, you are going to round to the fewest number of sig figs in general. So a worked out example we have, if you count the number of sig figs in 5.22, that is 3. 1.3 has 2. Which one has less? 1.3, which means our final answer will be rounded to 2 sig figs. So our unrounded answer is 6.786, but we only want 2 sig figs. So we are going to use a digit afterwards, the 8, to push the 7 up and rewrite our answer as 6.8. And you can see this explanation I wrote here. 1.3 has fewer sig figs than 5.22, so we are going to use that number of sig figs to contribute to our answer. Finally, here's an example. We have 180.2 divided by 3.3398. So 180.2 has 4 sig figs. 3.3398 has 5. Which one has less? 180.2. That is the number we are going to use to round our final answer. So you're going to plug this into your calculator, and you get a super long non-terminating number. I'm not going to write the full version because that would take too long. And in your future chemistry calculations, you would always just write the answer with the correct number of sig figs. We just first wrote the unrounded version so I could show you how the rounding would work. So as you can see in your calculator, we have 53.9553267. And we want 4 sig figs, so we would write that as 53.96 because we use the fifth significant figure of the 5 to push up the fourth significant figure, which is a 5, and make it a 6. Okay, so we have done multiplication, division, addition, and subtraction with significant figures in mind. Now we are going to move on to doing combined operations. And basically with combined operations, you want to apply the same significant figure rules and just follow order of operations and round at each step. So here's an example. We have 1.68 plus 2.5, and then that is being multiplied by 9.35. But as you can see, there are parentheses around 1.68 plus 2.5. So that is the calculation that we are going to do first. And with addition and subtraction, you can say it out loud with me. You round to the number that has the least amount of digits after the decimal place. So 2.5 has 1 digit after the decimal place. 1.68 has 2. So our answer for this addition part, which I wrote down here, is going to be rounded to 1 digit after the decimal place. And then you can take that number, multiply it by 9.35, and now we have a multiplication problem where we have 4.2 and 9.35. You want to use a number with the least amount of sig figs. So since 4.2 has 2 sig figs, our answer would be rounded to 39, which has 2 sig figs. Here's another example. You can look at this on your own, but basically I applied these significant figure rules to round to 17, and then did this problem separately, rounded to 4.8, and then 17 minus 4.8, round with the nearest decimal place, which is round to the number that has the least digits after the decimal place, which is 17 because it has 0. So I just rounded to 13. So with these calculations, you always want to make sure you keep unrounded answers in your calculator for future calculations so that you are not actually rounding twice, but you're just writing your answer for each calculation in a rounded form. And I will show you how to do that with these examples. So I'm going to grab my calculator. So our first practice, we're going to be adding 15.899 plus 2.3017. And this is a single operation problem, and I'm not going to write the unrounded version, but I'll just say it 18.2007, but we want to round to 18.200 because of the 3 digits after the decimal place in 15.899. Our second problem, we have 190.4 minus 60.5, and we want to round that to 129.9. It is more sig figs than 60.5. However, there's 1 digit after the decimal place here and one after here. So our answer has one number after the decimal place. Okay, this is a combined operation problem. So we are first going to multiply due to PEMDAS. So if we multiply 1.51 times 2.30, we have 3.473. So I'm going to round that to 3.47. I'm going to then divide by 3 to get 1 because 3 has 1 sig fig, so our final answer will have 1. Last problem, we are going to do 32 divided by 1.066, and that gives me 30.0187, blah, 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 blah. 32 has 2 sig figs, therefore our final answer will just be 30. Now let's say I wanted to use this answer in another problem, like divide it by 5. You would just want to, on your calculator, here's the answer you got for the first problem, just go on with your next function and divide by 5 to get your next answer. If you have an answer like way up in your calculator, you can just use your arrow keys, go up to the answer you want, and then press enter and apply your calculation that way. But you always want to keep unrounded versions in your calculator. So yeah, that is how you do combined operations with sig figs, and that concludes our second video. I hope you were able to learn something new in this video and that you got a better understanding of significant figures and temperature. In our next video, we are going to be going over density, so I hope you'll join me back. Please let me know if you have any questions in the comments, and I will do my best to answer them. And good luck with learning your chemistry.